So I last left you. We were talking about we're to have you find a sum. We're gonna have you find this factorial notation problem. Then we'll talk about cyclic notation. So to evaluate what this product is, we have 4 factorial times 11 factorial over 3 factorial times 8 factorial. And recall that I said that you find the highest one that's on the bottom and you write everything in terms of that. So thusly, we have 4 times 3 factorial, 11 times 10 times 9 times 8 factorial over 3 factorial times 8 factorial. Die. Those 8 factorials die, the 3's die there too. So, thusly, 3 times 4 times 3, thusly we have 4 times 9 times 10, which is 360, and you end up with 360 times 11. And I'm sure that all of you are really smart and can do that in your head, which is going to be 3,600 plus 360, which ends up being 3,360. So, or 3960. Sorry, I can't add today. So it's 3960. But yes, because 360 times 10 is 3,600. 3,600 plus 360 is 3,960. So there you go. Simple enough. Now let's talk about cyclic notation. So back to my fancy slides for a second here. Okay, cyclic notation is named after, of course, the Greek letter sigma, and it looks like a really fancy E, which we'll write in a minute. And cyclic notation tells us the following things. It tells us where to begin the sum, where to end it, what pattern the series follows, and to find the term prior to finding the sum. Okay, these are the 4 points of cyclic notation. And now that you can see this on a fancy screen, yay! I can show you what this looks like. The Greek letter sigma looks like this. Oh, I can write on my PowerPoints. Yeah. Alright. Alright. Looks like that. But anyways, let's go to your screen. Let's go to the next page. So we'll define sigma notation. Okay. So it looks like that. Sigma notation, also called summation notation, because quite frankly, writing this takes way too long. So we don't do that. Okay. So to define sigma notation, okay, the first n terms of a sequence, the sum, Some of the first n terms are represented by the sum. There's your Greek letter sigma from k equals 1 to n. It does not have to start at 1, by the way. You can start it anywhere. And then a sub n is equal to a sub 1 plus a sub 2 plus all the way to a sub n. Okay. So now I need to introduce you to some pieces here. Right? This piece is the index of summation. I is the index of summation, or k is the index of summation. Okay. K is the index. An index of summation is a fancy word for saying the beginning. Okay. Then we have n, which is the upper limit. N, which is the upper limit of summation. And of course, 1 is the lower limit of summation. And a sub n is, of course, the sequence that is defined, is the sequence which is defined. A sub n happens to be the sequence which is defined. Okay. These sequences have certain properties to them. So before I show you how to do these, we're going to go over. Before I show you how to do them, I'm going to give you the properties of how to work this. Okay. And the difference, and this is where we talk about the difference between a sequence and a series. Okay. The properties of summation, the properties of sigma notation are as follows. The first one, the sum from k equals 1 to n of some constant c is equal to c times n. Okay. Oops. Okay. So a constant, when you're taking the sum of a constant, it's just a constant times however many times you have it. Okay. The second property is that a constant can be factored out. The second property is that the constant can be factored out of the equation. Okay? So I can take a constant and take it out because everything is being multiplied by the same exact constant. We can do proofs of these in another video. Mm-hmm. The third property is the sum or difference. I'm going to combine properties 3 and 4, which are in the book. I'm going to combine them. The sum or difference of a series. Sequences can be added or subtracted together. Okay. So the sum is equal to the sum a sub n plus or minus the sum k equals 1 of n of b sub n. Okay? So you can add or subtract them. Multiplication, however, does not have that property. We don't multiply these. The last property, something that's illustrated in the study tip. Okay. Something that's illustrated in the study tip that you can express. You can always express your sums starting from 1 or 0. Okay. So the sum is equal to the sum. Sorry, this is a k. Of k equals 0 to n minus 1 of a sub n plus 1. Okay? So the last thing is that you can move the indices of summation from 1 to 0 or from wherever to as long as you subtract it. Or another way to write this is the sum of k equals of k is equal to j so j to n of a sub n is equal to the sum j minus m, n minus m, a to the n plus m. Like that. Okay. So I can move the indices of I can move it around and express the same sum. Okay. And since I didn't really express this well earlier, I'm going to quickly explain the difference between a series and a sequence. A series is a sum. Okay? The series is a sum of a sequence. Okay, that's one way to look at it. A sequence is the ordered pattern. So, to explain that in short, I can show it to you by example. The sequence 1, 2, 3, 4, 5, and not adding it together. The series would be 1 plus 2 plus 3 plus 4 plus 5. That makes sense. This is the sequence. That is the series. Okay. And so we can express really quickly, before we do an example, one more thing to express is we have an infinite series is expressed like this. The sum to infinity of n equals 1, doesn't have to be. Okay. Well, you usually start at 1. K equals 1. Of a sub n is equal to a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n plus dot dot dot. Okay. So that's an infinite, meaning it goes on forever, doesn't stop. A finite series stops at n, at k equals 1 to n of a sub n, a sub 1 plus a sub 2 plus all the way to a sub n. That's the difference between an infinite and a finite series. Infinite keeps on going. Infinite series stops when you get to the last number. Ironically, you can find the sum of both of them, but both require a different process. Okay. Now that you know the properties, we can quickly do some examples of how to add with these, of how to add with them. So let's find the sum. We're going to find the sum from k equals 1. Your books, you will usually use I, J, or K. I like K's, if you haven't noticed, from 7 of 4 times n. Or 4 times k, sorry. Okay. So to find this sum, we can do that really quickly. There is a shortcut. There is a shortcut which you learn later in the book. Don't use it now. Okay. I know some of you have probably learned this, know the shortcut to actually getting these problems done much quicker than necessary. But yes, you need to do it the long way before you can learn it the hard way, the easy way. So, to find the sum of that, we factor out the 4, and that's the sum from k equals 1 to 7 of k. So, solution is we factor out the 4, then we add the numbers 1 through 7. So that becomes 4 times 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. So 3 plus 7 is 10, 6 plus 4 is 10, that's 20, 25, 27, 28. And what 4 times 28? So that's 4, that's 2, carry the 3, so that's 100, so that's 112. Alright, easy enough. I will leave you to do these two on your own. Then we will discuss how to add an infinite series. So I will leave you to do these two on your own, and we'll do it when I come back. That's a 10, by the way. And I'll leave you to do this one as well. Alright, so we'll leave you to do those on your own. And we'll come back to those later.